Hey guys, so welcome back to another lecture video for Chem 115. This is the third part to buffer preparation calculation. And so far we've looked at two examples that demonstrates how to determine the volume or the mass to help prepare the buffer solution. And so we're going to go ahead and take a look at another example. And it's going to be a little bit different than the other two that we've worked through. So let's go ahead and read this problem. So we have a student that has 250 mils of 0.300 molar nitrous acid. The question is asking us, and so since this is a question, I'm going to highlight a different color. What is the volume of 6.00 molar sodium hydroxide that must be added to the solution to create a buffer? And it turns out that the pH, or the desired pH that we want this buffer to be, is 4.000. Last but not least, the Ka of nitrous acid is going to be 4.00 times 10 to the negative 4. And so what we're going to do is decompose this problem just a little bit more. We're going to take a step back and try to understand what's going on. And reading through the first sentence, this is the current concentration and volume that we have of nitrous acid. And so nitrous acid, it has one less oxygen than nitric acid. So this is going to be HNO2. And because this is not HNO3, nitrous acid is going to be a weak acid. Okay. And so if you guys did not know that, then that's okay because you have your acid ionization constant to fall back on. So the Ka of nitrous acid is 4.0 times 10 to the negative 4. Since it's less than 1, far, far less than 1, then it's going to be considered a weak acid. So just to visualize what's happening here, we have this beaker. And the volume of this solution is going to be 250.0 milliliters. And the contents inside this solution looks like it's pure HNO2. And the concentration of it is going to be 0.300 molar. Okay. And so currently as it stands, we just have one substance, which is a weak acid. And so having a weak acid alone does not make this a buffer. For a buffer to be formed, we need a weak acid plus its conjugate base. And so the combination of those two components inside our solution will give us a buffer. If you read through the problem, notice that the problem didn't really indicate the presence or the addition of the conjugate base. However, it is telling us that we're adding 6 molar concentration of sodium hydroxide. So we're going to go ahead and add NaOH. And so when we're adding this substance in solution, the sodium is going to separate from OH minus. So let me redraw this arrow here so that the hydroxide, which is the base of that specific compound, is going to react with a weak acid. And so overall, when you guys are thinking about this reaction, we have our base, which is going to be our hydroxide. And on the reactant side, we have a weak acid, which is HNO2. And so looking at it in the forward direction, this base will react with the ionizable hydrogen to produce water. And we're going to designate water in liquid state plus NO2 minus. And so the conjugate base that we're kind of searching for is actually produced from the actual reaction. So this conjugate base is only present when the hydroxide reacts with a weak acid. So hopefully you guys understand how I arrived to this chemical equation. So the question is asking us, if we have a 6.00 molar concentration of hydroxide, then how much volume do we need of it so that we can get a buffer? And the pH of that buffer should be at 4.000. Now I put in 2 units for volume here, milliliters or liters, or liters or milliliters, just because this problem didn't really specify. And so realistically, when you do this in lab, everything is in milliliters, and probably we should express our answer in milliliters at the very end. Okay. And so if you guys can imagine, your graduated cylinder is typically expressed in milliliters, as well as your volumetric pipettes, burettes, all of that stuff is in milliliters. All right, so now that we have an idea of what's going on here, we need to address this question. We need to figure out how much volume that we can, how much volume we have to use of sodium hydroxide so that we can get a buffer at pH of 4. I'm going to go ahead and focus on this unit right here, molarity. Okay. And I think my page is going to be a little bit messy, so I'm going to go ahead and kind of put this off to the side. And so for my sodium hydroxide, 6.00 molar concentration can be written as 6.00 moles for every 1 liter. And so by realizing the units that molarity can break down to for sodium hydroxide, if we can somehow cancel out the moles, if we can somehow cancel out the moles, then we'll get volume. And so what we're going to do is we're going to use molarity to figure out the volume of sodium hydroxide. So use molarity to calculate volume in liters. But for this to happen, I need to determine how many moles of the hydroxide should react with the weak acid, the nitrous acid. So how many, more specifically, initial moles? Right? And the reason why I said initial is because I'm initially putting in some volume of sodium hydroxide into my beaker. So what I want to figure out is how many initial moles am I actually putting in to react with nitrous acid. And so since I've mentioned initial, that should invite a very familiar friend that we've been hopefully grown accustomed to this semester, and that's the ICE table. And so if we can somehow determine the initial amount of hydroxide, then we can go ahead and use the molarity that was given to us for hydroxide to figure out how much volume we actually need of it. Okay. scoot this down just a little bit more. And so in this ice table, we can go ahead and ignore everything in the third column because it's representative of water, which is liquid in state. And so looking at this problem, do we know the initial moles of hydroxide that we're putting in? And the answer is no, we don't know. So we're going to have to put an X in my initial position. Do I know how many initial moles of nitrous acid I have in my beaker? Yeah, I should be able to figure that out. Here I have the molarity and here I have the volume. And so to figure out the initial amount of HNO2, I actually should not be putting this in bracket just because my unit is in moles. I'm going to take my volume, which is 250 mils. And so 250 mils is going to be 0.250 liters. So I'm going to take 0.2500 liters, and I'm going to multiply that by the concentration. And I'm going to express concentration in moles per liter. So that's going to be 0.300 moles for every 1 liter. Those units will cancel out. And the initial moles that I'll get for HNO2 is going to be 7.50 times 10 to the negative 2 moles. So by multiplying these two values, I'm making sure that their units is correctly correctly expressed, I can determine the initial moles of my weak acid, which is going to be 7.50 times 10 to the negative 3 moles. Now, we know that this base is going to react with this acid, but since we don't know the initial amount, in this scenario, we actually don't know how much of it is going to react. But we do know one thing. We do know that all of this base is going to be completely consumed. The reason why is because we're creating a buffer. And so if we're trying to create a buffer, we need a weak acid still present in my solution. So therefore, I cannot consume all of my weak acid. And so I'm going to go ahead and put in minus x for the change. And then I'm going to go ahead and put plus x for NO2. Now remember that this x is representing moles, because this is what we want to figure out. Now, real quick for NO2 nitrite, do we have an initial amount? No. And so the problem doesn't specify that we even have the conjugate base of the weak acid at all. And so therefore, we're going to go ahead and blank that out. And so if we add downwards, this is just 0. So we should have no hydroxide left over after this acid and base reaction has been performed. And in the equilibrium part for the weak acid, here we have, I don't think I created enough space for this, but 7.50 times 10 to the negative 3 minus x. So that is going to be the expression that represents the equilibrium amount. So this is going to be the equilibrium moles of HNO2. And so adding downwards in the last column, I just have x moles. of NO2 minus. Very similar to the advanced buffer calculations lecture video, if you observe that you have at equilibrium the presence of a weak acid and that of its conjugate base, then you have a buffer. And so if you have a buffer, you can go ahead and use the Henderson-Hasselbalch equation. And so the version that we're going to be using has to be the pH form because that's what they gave us in the problem. So pH is equal to pKa plus the log of the conjugate base over the weak acid. And so I'm going to go ahead and replace these words that I wrote down to the values that it represents. All right, and so looking at NO2, NO2 was my conjugate base, and so therefore this X is going to go in the numerator. Okay. So moles of NO2 minus. And I'm going to go ahead and take whatever I wrote here and put it in the denominator because that's representative of the weak acid, the moles of weak acid at equilibrium. So 7.50 times 10 to the negative 3 minus X. Cool. So now that I have everything in terms of mole units, I'm going to go ahead and plug in the pH and pKa. And so the pH, according to the problem, was 4.00. And so the pKa, so they didn't give me the pK, but they gave me the Ka. And so to determine the pKa, I'm simply going to take the negative log of 4.00 times 10 to the negative 4. So I'll go ahead and do that off to the side here. So I'm going to take the negative log of 4.00 times 10 to the negative 4. And so if I were to plug that into my calculator, I'm going to erase this. The value that I get is going to be 3.3979, and then there's a whole bunch of numbers. And so this is going to represent my pKa. I just took the negative log of 4.0 times 10 to the negative 4. So after I've plugged in all of my numbers, this just becomes algebra, and I'm just going to solve for x. And so the first thing I'm going to do is subtract this value to the other side. And the value that I get is going to be 6.020599, a whole bunch of other numbers. And so here in this case, if I treat this like a subtraction, if I apply the rules of subtraction of sig figs, then I need to report 3 places after the decimal. And so that's going to equal to the log of everything that you guys see here. So I'm just going to go ahead and quickly duplicate this so I don't have to write it again. And so to get rid of the log, I'm going to take the anti-log of both sides. So if you plug this into your calculator, what you guys will get is 4.000. Okay. And that is going to represent, or that's going to equal, moles of my nitrate. Actually, just to kind of speed things along, I'm just going to go ahead and just drop the units. So x over 7.50 times 10 to the negative 3 minus x. Okay. And so this looks like the mass action expression that you guys have been doing for quite some time. However, be very careful. Please do not ignore this bottom x like we typically did for mass action expressions. Just because notice the power here is x to the first power. It's not x to the second power. So you guys do not need to, you guys will not encounter a quadratic equation. And so you guys just need to solve for x by taking this whole term, this binomial, and moving it to this other side. So this is going to be 4.000 times this by 7.50 times 10 to the negative 3 minus x. And that's going to equal to x. And so you're going to go ahead and distribute that 4.00 to both of the terms that's inside the parentheses. And what you guys get is going to be 0.300 minus 4.00 I think this is going to be 0. Oops. So 4.00x is equal to x. And so we're simply going to add, 4.00x to the other side. And that's going to give us 0.300 is equal to 5.00x. And then I'm going to go ahead and divide these two values. And the value of x is going to be 6.00 times 10 to the negative 2. All right, so now that I have my value for x, I'm going to go ahead and plug this into my ice table. And remember the purpose of us building this ice table. It wasn't really so much to calculate the equilibrium concentration or find the pH, just like what we did in the in monoprotic acids and polyprotic acids and bases. However, the X is supposed to represent the initial moles of the hydroxide that we're supposed to put inside the beaker. And so since, I'll do this in pink, since X represents the initial moles of the base, all we need to do is use that value to determine the volume of sodium hydroxide that we need to put in. Okay? So we're really not trying to find the pH or anything like that because the pH is already given to us. Rather, we're going to go ahead and conclude from our ice table that X is going to, one of the values for X that it can represent is the moles of hydroxide. More specifically, the initial moles of hydroxide. And so if I wanted to figure out the volume, we're going to be using the concentration of this sodium hydroxide. And so the concentration is 6.00 molar. And remember, molarity contains units of moles and volume. And so I'm going to take 6.00 times 10 to the negative 2 moles of hydroxide. And I'm going to go ahead and multiply it by 6.00 moles for every 1 liter. Right? So moles per liter is molarity. So I'm still representing a 6.00 molar concentration. I'm just breaking down the units. Oops, actually I did it wrong. And so since moles is on the top side, we want to put moles at the bottom. And so this is going to be moles of hydroxide, and I need liters of hydroxide at the top. And so since molarity is moles per liter, for every 1 liter, that's going to give me 6.00 moles of the hydroxide. Okay. So now that our units cancel, we can multiply across. And the answer that we get is going to be 1.00 times 10 to the negative 2. And the unit is liters. And so cool. If we measure out 1 times 10 to the negative 2 liters, then that's how much of 6 molar sodium hydroxide is required to add to 250 mils of nitrous acid to create a buffer that has a pH of 4.00. Now, it's really hard for us to measure out 1 times 10 to the negative 2 liters. And let's go ahead and express this in decimal. So this is going to be 0.0, so 1, 2, so that's 0.0100 liters. And if I were to move this decimal 1, 2, 3 times, I get 10.0. Since I moved it 3 times to the right, that represents milliliter. And so 10 milliliters is something that we're comfortable measuring using a graduated cylinder or some type of other volumetric device. And so this is basically telling us is that if we measure 10 milliliters of 6.00 molar concentration of sodium hydroxide, and if we add that 10 mils into that 250 milliliter beaker, or that 250 milliliter solution that contains my nitrous acid, then I should be able to get a buffer. So some amount of this is going to be converted into NO2 minus, which is the conjugate base. And this whole system is now going to be a buffer. And if you measure the pH of that buffer, it should equal to 4.00. And so if it doesn't equal to 4.000 because of human error, measurement, etc., you guys can add small increments of the acid or the base depending on how far up or how far down you are from the target pH. Cool. All right. So hopefully you guys understood the main techniques to this problem. When you guys are doing this on your own, you guys are adding a strong base to a weak acid. And so that should invite you to write a chemical equation, just like what we did here. And then after you wrote the chemical equation, you're looking at, the question is asking, how much volume do you need to put in to this beaker? And so since that is representing like the very first step in the preparation of this buffer, what we're solving for is the initial volume, or translated into what this problem is implying for us to solve, what is the initial moles, right? So if we can figure out the initial moles, then we can go ahead and use the molarity to convert moles into liters, and then liters into milliliters. And since we wanted to determine the initial moles, that's inviting us to use an ice table. And when we get the equilibrium amounts of nitrous acid and nitrite, it produces a buffer. And so that should bring to mind the Henderson-Hasselbalch equation. And by plugging all of these values into the Henderson-Hasselbalch equation, we get the value for x. Cool. And then once we have the value for x, then we can go ahead and convert it to volume, which is what the question is asking us to solve for. All right, so we're going to go ahead and work through one last problem. And that's pretty much it for buffer preparation. So the last problem, let's go ahead and read it first. So what mass, okay. So in this scenario where we're trying to determine the mass of hydrochloric acid that would need to be added to 250 mils containing this concentration of sodium acetate and this concentration of acetic acid. And we're trying to get the pH to 4.250. All right, so once again, reading this problem, let's think about what's happening here. We're going to add hydrochloric acid into a solution. And the current volume is 250.0 mils. And so it turns out that this solution contains 0.500 molar concentration of sodium acetate. And so sodium is going to be a spectator ion, so I'm just going to represent acetate. I'm just going to represent only the acetate and not the sodium, because it won't affect the pH of my solution. And if you read the problem further, we also have another substance that's inside this solution, which in this case is going to be acetic acid. And so looking at the components inside this solution, we have acetate and acetic acid. And therefore, this solution is already going to be a buffer. So this is something different than, this is just a little bit different than the previous problem. In the previous problem, we only had one component to the buffer, which is HNO2. So if we are looking at the components that's inside this beaker, we have acetate and acetic acid. And so together, we already have a buffer. And so that's going to invite us to think about the Henderson-Hasselbalch equation. And so we're probably going to have to use that in our calculation somewhere, somewhere down the line. All right. And so looking at what we have here, we're trying to address what mass of hydrochloric acid we would need to add to the solution. So what we're looking for is the grams of hydrochloric acid. So grams is something that we can measure out using a balance scale. And now, when we're adding hydrochloric acid into this solution, something also happens. This hydrochloric acid, when added, it's not going to just float inside the solution. there's a reaction that's going to occur. And so HCl is a strong acid. And so we have an acid. And one of these components is going to be our base. And in this scenario, the base is going to be acetate. So we have the H plus from HCl. Remember that Cl minus does not affect the pH of the solution, so we can go ahead and completely ignore that in terms of what we're about to do. However, we're not going to ignore chloride completely if it's out of the solution, because we're trying to measure the mass of HCl. So the base in this buffer is going to be acetate, and acetate is going to be C2H3O2 with a negative charge. And so when you have the acid reacting with a conjugate base, that's going to produce the weak acid or the conjugate acid. And so if you are following the logic to this problem, we're initially adding some amount. And then there's going to be some reaction that occurs. So that's representing the change. And then after the change has occurred, the solution will then be at equilibrium. And so we're going to go ahead and depict the whole course of the reaction by using the ice table. And so here we have I, C, and E. And whenever we're performing these acid-base reactions, we want to convert everything in terms of mole units, not molarity. We don't really want to deal with volume, changes in volume, because that is going to push us to recalculate the concentrations using the dilution equation, and that's just extra work. And so what we want to know is how many moles of acid is going to react with moles of acetate to produce moles of acetic acid. So reading through the problem, notice that it didn't tell us any indication of how much acid we have. And so since we don't know how much acid we have, or what we're going to put into the solution, we're going to go ahead and represent that as X. Very similar to the previous problem. And so C2H3O2 minus acetate, we do have the concentration of it, and we have the volume. And so we're going to go ahead and multiply those two values after we convert milliliters into liters. And so for moles of acetate, we have 0.250. So I'm going to go ahead and convert milliliters into liters. Okay. So I'm moving that decimal place 3 times to the left. And I'm multiplying it by the concentration of acetate, which was 0.500 moles for every 1 liter. Okay. So I grab that number from the problem. Okay. And so that's going to give me 0.125 moles of acetate. And I'm going to go ahead and start abbreviating acetate as AC negative. Okay. Just so I don't have to write the whole word over and over again. And so I'm going to go ahead and put in 0.125 moles of acetate. Now, here in this case, recall that we already have a buffer. And so I know that there's like a lot of stuff here. It's getting busy. So let me just zoom in real quick, and I'm going to erase some stuff. And so everything here in this solution is already a buffer. So what that means is that we have an initial amount of acetic acid, and we have an initial amount of acetate. And we already solved for the initial amount of acetate, it's 0.125. Now we need to solve for the initial amount of acetic acid. Now, since the volume and the concentration is the same as that of acetate, the value is going to be the same as well. So the initial moles is 0.125 for acetic acid. And I'm going to represent acetic acid as HAC, while this is going to be AC minus. All right. And so because we want to make a buffer, and the buffer always requires the weak acid and its conjugate base, then we know that the amount of hydrogen ions or acid that we're adding into the solution is not going to completely consume all of the acetate molecules that's found inside the buffer. In other words, the change is going to be less than the initial amount for the acetate. Okay. And so we do know that when an acid-base reaction occurs, both components gets consumed, but the limiting reagent, if you will, gets completely consumed. And so therefore, if you add down, we're not going to have any hydrogen ions at equilibrium. And so this is going to be minus x, and this is going to be 0.125 minus x. And this is going to represent the moles of our acetate. In this case, we're going to produce some amount of acetic acid. And so this is going to be 0.125 plus x. And that's going to represent the moles of acetic acid. And so this expression is going to represent the equilibrium amounts of acetate and acetic acid. And once again, since acetate is a weak base and acetic acid is its conjugate, and since we have both of them still present at equilibrium in our solution, then we can go ahead and use the Henderson-Hasselbalch to determine the initial amount of moles of hydrogen ion that we have by solving for x. And so I'm going to scroll up. Notice that they gave me a Ka value, and they gave me pH. And so I'm probably going to use the pH equals to pKa version of the Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of, in this case, remember the numerator is always going to be the weak base. So I'm going to put an A minus, and then HA is always going to be at the bottom, or the conjugate acid, or the weak acid is going to be at the bottom. And so this is going to be 0.125 minus x. Okay, so I'm going to plug that into the numerator. And since this is my acid, I'm going to plug that into my denominator. All right, and so here I have my pH. My pH is equal to 4.250. That's my pH. And so my pKa is going to be the negative log of 1.7 times 10 to the negative 5. And so if I take the negative log of 1.77 times 10 to the negative 5, punch that into my calculator, the value of my pKa that I'm going to get is going to be 4.752. So this is 4.752 plus the log of 0.125 minus x over 0.125 minus x. So now I'm simply going to solve for x by using rules of algebra. So I'm going to move this guy over to the other side. That's going to be negative 0.502, which equals to the log of 0.125 minus x, 0.125 plus x. So I'm going to go ahead and take the antilog, both sides. I'm going to punch that into my calculator, and then I'm going to get 0.31477, a whole bunch of numbers. That's going to equal to 0.125 minus x over 0.125 plus x. I'm going to take this whole term, multiply it to the other side. So I get 0.31477 times this by 0.125 plus x, which equals to 0.125 minus x. So I'm going to go ahead and distribute. And so when I multiply the first number, when I multiply 0.125 by 0.31477, so by the way, in terms of sig figs, I'll just go ahead and highlight how much I'm going to be keeping at the very end. So it looks like I still have 3 sig figs. So this is going to be 3.93 times 10 to the negative 2 plus 0.31477 times x. That's going to equal to 0.125 minus x. And so at this point, I'm just going to rearrange some terms. So first I'm going to subtract out that 0.125. And so what I get here is going to be negative 8.56 531. There's a whole bunch of numbers. Times that by negative 2 times 10 to negative 2 plus 0.31477 x, which equals to negative x. So I'm going to subtract 0.31477 x to the other side. Okay. So that's going to be negative 8.56531 times 10 to the negative 2, which equals to negative 1.314777x. So please don't forget that the x can be written as 1x. And so you're going to go ahead and divide this to the other side. And so therefore x is going to equal to 6.51468 times 10 to the negative 2. And if you guys recall, x is supposed to represent not only the change, but more specifically. So x does represent the change. But with respect to the question that we're trying to address, it's representing the initial moles of the hydrogen ion that we're going to add to the solution to make this buffer at 4.250. And so X is going to represent the moles of H plus, which originally came from hydrochloric acid. And since that value is going to be 6.51, I'm going to start using 3 sig figs. 6.51 times 10 to the negative 2. I can go ahead and use this value and perform some stoichiometry to convert moles of hydrogen ions. Remember, this is the initial moles of hydrogen ions that I'm putting into my solution, and convert it in terms of mass. And so to do that, I need to make sure that I convert it back to hydrochloric acid. And so the problem is asking how much mass of the hydrochloric acid is being added into the solution. And so once it's inside the solution, then it dissociates into H plus. But when we're solving backwards, when we're trying to determine the mass, we have to include that chloride because that chloride did not dissociate from the hydrogen when it's still solid. Right? It's only when you add it to the solution that will allow hydrogen to be separated from chlorine. So for every 1 mole of H plus, that equals to 1 mole of HCl. Okay? So if you're looking at the chemical formula for HCl, we have a 1-to-1 ratio. And so since we want to determine the mass of HCl, I'm going to put grams of HCl at the top, moles of HCl at the bottom. So grams and moles, that should invite you to think of molar mass. And so the molar mass of HCl is going to be 36.461 grams per mole. And once again, you guys can calculate this from the atomic mass found in the periodic table. So for every 1 mole, that's equal to 36.461 grams of hydrochloric acid. And so if you multiply everything across, the mass that we get is going to be 2.38. So this is the correct number of significant figures, grams of HCl. So what this is telling us is that if we measure out 2.38 grams of HCl using a balance scale, and if we add it to this buffer solution, then the pH of that buffer solution is then going to be 4.250. Okay. All right, so hopefully going through these 4 examples, you guys have a better idea of how to tackle these buffer preparation problems. I encourage you guys to perhaps go back to every single one of these parts of the videos, pause it such that you guys just only see the question and just try to work it out on your own. You can always fast forward the video to look at, individual pieces of the work or to look at the final answer to make sure that you are on track. So the next set of videos talks about titration curves. So I'm going to start discussing titration curves. And so titration curves, they are more or less an amalgam of all of the different techniques of solving for pH, concentration, etc., that we've kind of gone through this whole chapter. And so the titration curves it's not a new item. We've already done every single one of those parts. However, we're just going to put it together to create our titration curve. And so I'll go ahead and stop the video. I'll see you guys next time. Bye.